Hello guys. So now we are going to discuss about discrete mathematics. So in discrete mathematics, these are all the topics that we are going to cover. So before discussing about all these topics, I just want to give a small introduction about why and what is the necessity of studying this discrete maths. Okay. So discrete maths plays a very important role in all the computer languages and computer hardwares what we are using. That is the programmers and the designers we are using. So in mathematics, if you see, we will be studying about discrete mathematics, right? So there what we will be doing, we will be playing with numbers, that is mathematical formulas, algebraic formulas, trigonometric formulas. For what purpose we are using all these things? Okay, in order to derive some result or to derive some output. So the same thing in computer science field, discrete maths plays a very important role. That is behind the screen of each and every subject that we are studying, we are manipulating with numbers. Okay, so in order to manipulate with numbers, we need this evaluation of discrete maths. So this is a very important subject what we must have to study in order to implement in all the computer science subjects, not only in computer science subjects, in all the subjects that we are going to study in various fields, right? So this is a short introduction about DM. So now we will go about different topics, right? So in the first topic, we are going to study about operations on relations, right? And then properties of binary relation and equivalence relation, and then a representation of a matrix using relation and representation of a relation by diagram, functions, range of function, classification of function, composition of function, and invertible functions. So all these things we are going to study, friends, right? So now we will start with the first topic. So before that, you should know what is called as a relation. In order to do any type of manipulation between the values, we must have to know what is the relativity that is being present between the values. For example, if I want to do some addition, I need a connection between two numbers. If I have two numbers only, I can add. Even for multiplication, if you see, for example, I am talking about, if I want to do some multiplication, I need combination of two or three numbers joined together so that I can do some operation on it. Okay, so that is called as a relation. So relation will never act as a single value. So there must be a friend or a connection between different values so that I can make some result out of it. Okay, can you follow? So there are different types of relations that we can make using values. So ternary relation, unary relation, and so on. So here we are going to study only about binary relation. What is the use of binary relation? So binary relation is nothing but we are going to do some mapping between two pairs. So set A and set B, right? So we are going to consider only pair values that are present between two sets. That is, we are going to deal only with values that are present in two different types of a set. Okay, so how we are going to create some relationship between these values are by using this A cross B. Okay, so A cross B is nothing but in mathematical environment we will be using matrix calculation, right? So multiplication of two matrix. So similarly, we are going to deal with the values in order to make combination of different values using this Cartesian product. Okay, so a relation is nothing but we are going to set up a connectivity between the values present in one set to the values present in another set by using a Cartesian product value which is nothing but A cross B. Okay, then we are going to express those relative values using ordered pair. Okay, so by using ordered pair, we are going to represent these relationships. So in binary relation, we are going to represent the set of values by using ordered pair. So which is nothing but x comma y belongs to R. So relation will be holding some connectivity between the values. For example, 2 into 3, what will be the value? It is 6. So 2 comma 3 is a having certain connection so that it is going to produce a value called as 6. Can you follow? So x comma y belongs to R where x is related to y. As I told, 2 into 3 is equal to 6. How we are getting that value 6? 2 is related to 3 or 3 is related to 2. So based on that only I am getting the value, right? So that relationship is being exhibited by using this formula, which is nothing but ordered pair. It is not even called as a formula, it is a format. Okay, so what are the different types of operations that we can perform on relationship is same, friends, that is mathematical relationship. Okay, we are doing in different types of operations on sets, right? Have you all studied this one? For example, union, intersection, difference, complementation, and so on. We are doing all these operations in mathematics with values that is being mingled on it, right? So what is called as a union? So union is nothing but we are going to take values that is present in two different set of sets that is being given to us, and we are going to do the union of all the operations. What is called union? What is called union? So union is nothing but we are going to combine the values of set R union set S. Okay, so we are going to combine and write all the values. That is called as an union. Similarly, what is called intersection? So intersection is nothing but R intersection S for an example. So we are going to take out all the common values that are being present between the sets R and S, right? So what is called difference? R minus S. We are going to take the answer from the two sets R and S. So what is the format? It is R minus S. So what is R minus S? The values that is being present in the relationship, in the set R should not be present in the set S. Can you follow? So those values will be occurring as your output. Okay. So what is called complementation? So S minus R, that is reversal of R minus S. Okay. So what is the meaning? So those values that is present in the set S should not be present in the set R. Okay. So this is called as complementation. So all these things you might have studied in mathematical operations, right? So these are all the different types of basic operations that we'll be doing in relations. Okay. So now this is the main part for doing some process on the pairs. Okay, see, this is called as a Cartesian product value. So see here we have represented two types of relations, R1 and R2. So R is nothing but relation 1, R2 is nothing but relation 2. So R1 is holding certain values, that is 1 comma A and 2 comma B. Okay, so what is called R2? So R2 is another relation which is having the ordered pair value 3 comma C, another ordered pair value 4 comma D, and another ordered pair value that is called as 5 comma E. So meaning for representing like this is 1 comma A is related within each other in some means. Okay, so similarly 2 comma B is related within each other. It doesn't mean that 2 is related to A or B is related to 1. Can you follow? So we have discovered this relation 1 in such a way that there is certain relationship that is being present between 1 comma A. Similarly, there is certain relationship that is present between 2 comma B. Similarly, for R2 also we have got 3 comma C as one ordered pair, 4 comma D as another one ordered pair, and 5 comma E as another one ordered pair. So we are going to use this pair values in order to do certain operations for implementing discrete mathematics operation. For example, I want to find intersection, I want to find union, complementation, difference, and so on. So in order to do or implement that operation on these ordered pair values, I need certain generation of things. So this is the generation. Okay, so how I am getting this combination is by using this R1 cross R2. In order to implement discrete mathematics operations on different set of values that is being present in R1 and R2, the first and foremost step that I want to do is Cartesian product. Can you follow? So after doing this Cartesian product only, I must have to implement the future process which we are going to discuss in the future. Can you follow? Right. So now, how to implement this Cartesian product? See, let relation R1 contain 2 tuples and relation R2 contains 3 tuples. So what is the meaning? So total number of rows, see, rows is nothing but in DBMS we'll be studying, right? Relation is nothing but table. So table consists of rows and columns. So similarly, here we are also representing the same word tuples, but that tuple deals with total number of ordered pairs that is being present in a relation. Here, the tuple represents the total number of ordered pair values that is being present in a relation. Can you follow? So, the total number of tuples in R1 is 1, A, one row, and 2, B is another one row. Similarly, R2 contains 3 tuples. 3, C is one row, 4, D is another one row, and 5, A is another one row. Okay, so if I do this Cartesian product, what are all the different types of combinations that we are going to deal with in future are got. So see, 1, A is joined with 3, C, 1, A is joined with 4, D, and 1, A is joined with 5, E. Friends, can you follow? Right. So 1, A, 3, C is one pair, 1, A, 4, D is another one pair, and 1, A, 5, E is another one pair. So this is being represented. Okay. So next you see 2, B, 3, C is another one pair, 2, B, 4, D is another one pair, and 2, B, 5, E is another one pair. So we have got a new relation R1 cross R2 where this is one tuple, 1, A, 4, D is another one tuple, 1, A, 5, E is another one tuple. Students, as we will be doing in normal matrix multiplication, here also we are combining rows with different types of columns present. Same thing, here we are not doing any actual multiplication, here we are combining the values, that is a major difference, right? Okay, so this is the result that we are getting after doing or getting a new relation which is nothing but R1 cross R2. Just now we discussed about what is the meaning of Cartesian product and what is the reason for implementing that Cartesian product. So under this Cartesian product, we are going to see different types of relationships that we can apply. Okay, so what are all the different types of relationship that I can apply on the Cartesian product result that I have got. So generally what is called as a relation, just now I explained. Suppose if I take as a family, okay, we will have different types of relations. Father, mother will be one relation. Husband, wife will be one relation. Mother, son will be one relation. Okay, there are different types of relations that I can generate by using a single word that is called as a relation. So how different types of relations are being formed? So that different types are being given here. Okay, so first type of relation that we can make is identity relation. Right? So what is called as an identity relation? So the meaning of identity relation is if it contains only ordered pairs where every element of set A is related to only itself. Can you follow? So if I have a relation, okay, in that relation there will be some values 1, 2, 3, 4 like this. There are certain values. Okay. So identity relation is nothing but the value is having a relationship within itself. Okay, for example, you take in a human being, there are orphans. Okay, who is an orphan? Who is not having any relationship? It means he is related to himself. Can you follow? So he is related to himself. That is the meaning of identity relationship. A value that is being related to itself is called as identity. So this is one example. So see here, A is equal to 1, 2, 3. So identity relationship has to be generated in such a way that value is related to itself, right? So 1, 1 is related to 1, 2, 2 is related to 2, and 3, 3 is related to 3. None of the other relations is not possible here. Okay, see 1 is related to 2. Is this present? No. So only 1, 1, 2, 2, 3, 3. So this is called as an identity relation. None of the other relations will be accepted here. Friends, right? Okay. So now we will go for reflexive relation. Now what is called as a reflexive relation? A reflexive relation is such that every element of A is related to itself. Okay, so that is called as a reflexive relation. So the meaning of reflexive and identity is somewhat same. Okay, in identity relation you see only these elements are present, right? But in reflexive relation, these elements will also be present as well as other relationship will also be present. Okay, for example, you see we can take the same element, okay, 1, 2, 3. So reflexive element will hold all these results, that is 1, 1, 2, 2, 3, 3. That relationship will be held. Similarly, along with that, if there are certain elements like 2, 3, 1, 2 is being given in this bracket, so that is also accepted. Can you follow? So that is called as a reflexive relation. So along with identity relations, if there are extra relations that is being present, for example 1, 2, 2, 3 is present, so that is also accepted. So that is called as reflexive relation. Okay. So another thing is that these types of relations, right? So 1, 1, 2, 2, see this one. So 1, 2, 2, 2, then 3, 3. So all these are called as diagonal pairs because both the sides are having the same values, right? So we are calling these types of elements as diagonal pairs. So reflexive element will have the combination of both the diagonal elements as well as non-diagonal pairs. So here you see, so this is one example of reflexive relation. So these types of questions only you will be getting, and they will ask you to find whether it is a reflexive, symmetric or anti-symmetric like this. Okay, so all these things we will discuss in the future. That is in the next screen. So take this as an example. Okay, so n is a set of all natural numbers and a relationship is given as a comma b. A comma b may be any value such that a is equal to b. It is a reflexive relation. So how can you prove this? So now what is called as a natural number? So natural number is nothing but 1, 2, 3, 4, 5, 6, etc. Okay, all these are called as a natural number. Okay, so how we can make this sentence as true? I am going to take two values, right? 1 and 2. 1 is also a natural number, 2 is also a natural number. Yes or no? So 1 is also a natural number and 2 is also a natural number. So I can tell that 1 natural number is equal to 2 natural numbers, right? So this is a reflexive relation, right? Can you follow? So 1 is also a natural number, 2 is also a natural number. Therefore, I can tell that A is equal to B. Okay friends, so now I am taking another one natural number, for example 4. So 4 is also a natural number. I am writing in the format as 4, 4. So keenly observe, I am writing it as 4, 4. So what is the meaning? 4 is a natural number and another one 4 is also a natural number. I can make the relativity, isn't it? So 4 is equal to 4. Okay, so all these combinations are satisfied for a natural number in reflexive relation. So I can tell that set of all natural numbers are all belonging to a category which is called as a reflexive relation. Okay friends, are you all clear? Okay, so now we will go for another type of representation of relation. So it is called as symmetric relation. So what is called as a symmetric relation? Okay, so see in this definition itself you can be able to understand. If there are elements in set A, so which is nothing but A1, A2. So there are two elements values, that is A1, A2. If I want to make as a symmetric relationship, meaning is if A1, A2 pair is present in the relation, then its reverse. What will be the reverse? A2, A1, isn't it? A1, A2 now, its reverse is A2, A1. So both must be present in a relation. So it is called as a symmetry. Okay, so now I am taking one element, that is 1, 2, 3, 4. Okay, so I am going to make a relationship. So in that relationship, if I am writing as 1, 2 is a relation, it must hold 2, 1 also. Suppose 1, 2 is present and 2, 1 is not present, means it is not coming under symmetric relationship. Can you follow? Right. So now you take another one example, meaning is diagonal pairs. So in diagonal pairs, I am telling as 2, 2 is present in a relation. Can I write in a reverse manner? If I write in the reverse manner also, I will get as 2, 2. Can you follow? So 2, 2, if I write in one time, if I reverse it also, I am getting 2, 2. So meaning is indirectly both are equal. Symmetric relation will accept the values having A1, A2 as well as A2, A1 along with the diagonal pairs. Okay, because it will be written only once, because 1, 1, if I write again 1, 1 also, it is going to produce the same value. So it is represented as in a one pair. Okay, so symmetric relation will hold. Okay, the elements of A1, A2, its reverse along with the diagonal pairs. Okay, so that is another one example. You see, John is the brother of Sam. So this is one example. So I can also tell that Sam can also be a brother of John. So brother is a common term. John is a brother of Sam or Sam is a brother of John. Right? Can you follow? So both should be true for a symmetric relationship. Okay friends, can you follow? Right. So now you see again the natural number is also an example for symmetric relation. So how you are telling a natural number is a example for symmetric relation, because 1, 2, 3, 4, 5 all are going to be a natural number. Okay, so if I tell 1, 2 is a natural number. Okay, if I take as 2, 1, 2, 1 will also be a natural number. Can you follow? So both are true. Again you see 1, 1. 1, 1 is a natural number. Again if I reverse and write 1, 1, so that is also going to produce a natural number. Can you follow? So natural number is also comes under symmetric relation. Okay, so now we will go for anti-symmetric relation. So what is called anti-symmetric relation? Just the opposite of symmetric relation. See, very easy. If A comma B is present in a relation, then its reverse should not be present. Can you follow? If A comma B is present in the relation, its reverse should not be present. Okay, so that is called as an anti-symmetric relation, but diagonal pairs will be accepted. Okay, see 1, 1 is present in relation, and then because again 1, will not be present. Can you follow? So 1, 1 is the same value. It is a diagonal pair. We are representing it as a single value. So it can be accepted in anti-symmetric relation. So this is one example for anti-symmetric relation. So see here, I am taking two values a comma b. So the condition is a less than or equal to b. So this is my condition. How to check whether this is an anti-symmetric relation? You take two values. Okay, I am taking the value as 3, 4. Okay, I am taking the value as 3, 4. Now tell me whether 3 is less than or equal to 4. Condition is true. So 3 is less than or equal to 4. Condition is true. Now tell me whether 4 is less than or equal to 3. See, reverse should not be present in antisymmetric, right? So 4 is not less than 3. So this condition is false automatically. So this is satisfying the condition. See, 3 is less than equal to 4. Now it is accepting. Similarly, 4 is not less than or equal to 3. So both the conditions should be satisfied for antisymmetric relationship. Students, can you follow? So I am taking two values a comma b, where a is equal to 3, b is equal to 4. So the condition should be a is less than or equal to b. See, obviously 3 is less than or equal to 4. Condition is satisfied. Okay. Similarly, what is the reverse value? 4 less than or equal to 3. 4 less than or equal to 3. So that should not be satisfied. Yes, it is not satisfied. Therefore, it is going to belong to antisymmetric relation. Okay. So next you take a is equal to 1, b equal to 1. Okay, so a equal to 1, b is equal to 1. So now you check the condition, 1 is less than or equal to b. Okay, so meaning is this condition is true. Okay, so diagonal pairs always will be accepted in antisymmetric relationship. Okay. So now we will go for asymmetric relationship. So what is called asymmetric? So asymmetric is equivalent to antisymmetric. Okay, so asymmetric relationship is equivalent to antisymmetric, but only one condition. See, diagonal pairs are not allowed. Please make a note of it. Okay, so asymmetric relation is equal to antisymmetric, and the meaning is the diagonal pairs are not allowed. Okay. So next we will go for transitive relationship. So what is called transitive relationship? So if I am going to have a set A holding the elements A1, A2, A3. So the transitivity relationship is if A is equal to B and B equal to C. So the meaning is indirectly I can tell A is equal to C. Yes or no? So that is called as a transitive relationship. Okay. So you take the elements set A. Okay. So set A has the values pairs as A1, A2 belong to R. Similarly, if A2, A3 is belonging to a relation R, then I can tell that A1 and A3 is also belonging to the relation R. Okay. Can you follow? Right. So A1 comma A2 is in the relation and A2 comma A3 is in the relation. So there should also be a pair which is A1 comma A3. So all these three pairs should be existing in the relation. So suppose if this type of pairs are present, then it is called as a transitive relation. So we can take one example. If P, Q, R are three persons such that P is a friend of Q and Q is a friend of R. So then I can tell that P is also a friend of R, right? Yes or no? Yes. So P is a friend of Q and Q is a friend of R. So indirectly it means that P and R are close friends. Can you follow? So this type of existence is called as a transitive relation. So here another one example. Similarly, take a natural number. Okay, so there are n number of natural numbers present. Okay, so how we will match this relation? If this is the condition, so a comma b is a natural number. How we will check whether it is a natural number? Take three values 1, 2, 3. Okay, take three values 1, 2, 3. Okay, if 1 is a natural number and 2 is a natural number. Okay, again if 2 is a natural number and 3 is a natural number. So I can tell 1 and 3 is also a natural number. Can you follow? So like this only we should have to make a comparison. Now what is called equivalence relation? So equivalence relation is nothing but if a relation is going to satisfy reflexivity, symmetric and transit relation. If all these relationships are being satisfied in a relation, then it is called as an equivalence relation. Okay, so example we discussed about natural numbers, isn't it? So in all the natural numbers example that we took, so that it satisfied reflexive relation, symmetric relation as well as transitive relation. So it means natural number pair is going to be an equivalence relation, friends, right? So now what is called as an empty relation? Meaning is none of the elements in the set are having any relationship with any other element in the set. Okay, that is called as empty relation. That is, values in a set are not making any relationship with another set. So that is called as an empty relation. See, this is one example for an empty relation. If A is a set of students of grade 8. Okay, so this grade 8 students are all boys. It is a boys school. So that is a relationship being given as R is equal to A comma B, where A and B are sisters. Can I make any relationship? See, condition is sisters, but here they have given as boys school. How can I segregate the values of girls? It is not possible. Okay, so A and B cannot be the sisters. Okay, because it is a boys school. So if I'm going to generate any statements from this boys school data, it is going to produce only an empty value, right? So this is an empty relation. So now we will go for universal relation. So what is called universal relation? Universal relation is equivalently we can represent it as a Cartesian product. So what are all the possibilities of pairs that I can make from a set? It is called as a universal relation. Okay, so take this an example. Let A is equal to 1 comma 2. Okay, so this is some printing mistake. Okay, slash is being given. Don't consider that. Take as A is equal to, within flower bracket it is 1 comma 2. So what are all the different combinations that I can get from this relation A cross A is 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2. So all the possible pairs are called as your universal relation. So these are all the general brief discussion about binary relation. So we have discussed about reflexivity, symmetric, transitivity, antisymmetric and irreflexive. Okay, so all these things I think you'll be having a clear idea. What is irreflexive? Okay, irreflexive is opposite that of reflexive. So it will hold only those values where A is not related to A. Meaning is it will not accept diagonal pairs. But in reflexive, it will accept diagonal pairs as well as the additional elements. So now we will see what is the representation of relation by using matrix. So we can represent the relation, that is all the ordered pairs, by using two types. One is by using matrix form, then another one is by using directed graph. So this is a simple representation. Okay, if an ordered pair is present in a relation, we are representing that intersection of row and column as 1. Suppose if that ordered pair is not present in a relation, we are representing that intersection of row and column as 0. Can you follow? So see, if there is a relationship between A and B, okay, it is represented as 1 and 0. See here, if A is related to B, if there is an ordered pair, it is 1. If there is no ordered pair, then it is 0. We will see with an example. So A is equal to 2, 5, 6. Okay, so this is one value, set value. So among this set value, we have generated a relation. Okay, 2, 2, 2, 5, 5, 6 and 6, 6 on A. This R is a relationship from A into the same set. Okay, we are creating a relationship from the set A to the set A itself by having the value as B. Okay, first set is represented as capital A and the another set of set A itself is represented as capital B. So, each value we are giving some variable name. See, A1 is equal to 2, A2 is equal to 5, A3 is equal to 6. So, these are all belonging to set A of 2, 5, 6. Now, B1 is equal to 2, B2 is equal to 5 and B3 equal to 6. Okay, so these are all some set values, variable names that we have assigned for set B, which we got from the set A relationship itself, friends, right? So now, for this pair 2, 2, 5, 2, 5, 5, 6 and 6, 6, we are going to generate a matrix value. So now I am telling as 2 is 2, 2. So this is one ordered pair 2, 2. How we are going to represent it in a matrix? So first one is A, okay, A1. Then this is also B1. Okay, so A1, B1. See, A is 2 and B1 is 2. So A1, B1. So first row, first column is 1. So because here 2, 2 is existing. So next you see 2, 5. So A1 is 2 and B2 is equal to 5. So this is A1, B2. So first row, second column. So it is 1. Similarly, you take 5, 6. What is 5 value? 5 value is A2. Okay. And what is 6 value? So 6 value is B3. So A2, B3, that is second row, third column. Can you follow? Right. So next you see 6, 6. So where is 6 is present in A3? Here in B, where is 6 is present? In B3. So A3, B3, that is third row, third column. So here I am representing it as 1. So remaining all the places are all 0. Can you follow? Right. So this is a way for representing another form. It is directed graph. So very easy. Okay friends. So if 1, 2 is present now, you should have to draw a directed edge from 1, 2. So 1 to 2, I am drawing an edge. Okay, it means that 1 is related to 2. Next ordered pair you see 1, 3. So means 1 is related to 3, not 3 is related to 1. So in order to represent that relationship, we should have to draw a directed arrow from 1 to 3. So next you see 1, 4. So there should be a directed edge from 1 to 4. So 1 to 4. Similarly for 2, 3, so there is a relationship that is being present from 2 to 3. So here it is being added. So next you see 2, 4. So from 2 to 4 only there is a relationship, right? So 2 to 4. Next is 3, 4. So 3 to 4, right? So we have represented. So this is a directed graph for the ordered pairs. So in the previous screen, we discussed about how to draw a matrix by calculating the edge value 1 and 0. So here we are going to find out the directed edge. That is, we are going to draw a graph where the directed edge represents a relationship from starting to ending pair.